once we're able to construct a molecular orbital diagram for a heteronuclear diatomic molecule, it now becomes possible for us to ascribe an electronic configuration to essentially any diatomic molecule. And I've written one up here for nitric oxide, which is part of the examples that we gave in an earlier video. So this is one way that we can express the population of the electrons in a molecule, in a diatomic molecule. However, once again, if we really want to get down to the heart of the states that these electrons inhabit, we'll need to characterize these in terms of their angular momenta. Now, we did this with term symbols with atoms, so let me remind you that in the atomic case, we would have term symbols that were constructed more or less like this, where the S was the spin of the electrons in the atom, L represented their angular momentum, the orbital angular momentum, and J was the total angular momentum. And we found that, in fact, a range of different L values could result, well, a range of all of these values could result, and there were certain rules that we had for dictating the ranges of values that we would have. Well, it turns out that we can do something very similar for a diatomic molecule. But the term symbol will look similar, but it will have a few differences that we should be aware of. All right, first of all, it will have a spin multiplicity part, which would be given by 2s plus 1. But now instead of L, we're going to use a molecular angular momentum, azimuthal angular momentum, lambda, as we've defined it before. We'll describe the total angular momentum using omega. Don't worry about the notation. This is one way of teaching you the Greek alphabet, I suppose. But there are some other things that we can add to this term symbol for molecules that are actually important in various cases. For example, if it's a homonuclear diatomic, we may be interested in knowing whether the term symbol has G or U symmetry with respect to parity. There's another particular symmetry that we're sometimes interested in, and that's the reflection of the wave function through a plane that contains the internuclear axis. I'm not going to really talk a lot about this one, but it's worthwhile for you to be aware of it. This typically is used only when our lambda parameter is 0. Okay, now you will recall that for the atomic term symbols, when L was equal to 0, 1, 2, 3, and so forth, that in fact we gave these things different letters. And so instead of writing the number here for L, we wrote the letters. And we had S for L was equal to 0, P when it was equal to 1, D when it was equal to 2, and F when it was equal to 3. A similar arrangement is made for this, for diatomics, and that is as follows. Again, these are possible values for lambda, and the labels that would use to designate these things correspond to sigma, and that's capital sigma, capital pi, capital delta, capital phi. Now, in case you're wondering, yes, these are the Greek equivalents to these 4 letters that we use to designate for the atoms. So when we go from atoms to molecules, we basically go from Roman letters to Greek letters. I hope you appreciate that this is also a foreign language lesson for you. All right, so what do these various things mean in the diatomic molecule term symbol? Well, S has the same meaning. It is the total spin for a given state that we're capturing within the term symbol. All right, the lambda represents the azimuthal quantum number. And remember, that's the quantum number relative to rotation about the axis of the molecule. So if the molecule is on the z-axis, it's the rotation about this. Gives rise to the value of lambda. All right, now, before we gave these things like values of lambda equals 0, we're going to care now about both senses of rotation, that is rotation as I've drawn it here, and rotation in the opposite direction, which would be here, in which case we're going to have different signs. Now, for the case of lambda equals 0, there's only one possible sign, and that's 0. But if I get to lambda equals 1, I can have rotation in the positive sense and also in the negative sense. So I'll have these two different values of m sub lambda, and we've actually seen those in an earlier video as well. Now I'll note that there is no m sub lambda equals 0 that corresponds to lambda equals 1. And the reason for this is that this would correspond to the state where we have a p orbital lined along the axis for the molecule. And so this is going to form a sigma bond for which lambda is equal to 0. So we can't have one of these when we're talking about lambda equal to 1. We can only have pi bonds, and so we only have 2 possible pi bonds, so this is the degeneracy for that. We would find a similar thing would happen if we had lambda equal 2. There would only be 2 possibilities, m sub lambda equal plus 2 and m sub lambda equal minus 2. All right, I mentioned that this omega represents the total angular momentum. We're not going to do much with this, but I'll note that as a first order approximation, this ranges in value from the absolute value of lambda minus s to lambda plus s. And this again, it appears as a subscript on the term symbol. We'll express term symbols both with and without this parameter denoted. We've talked a little bit about the G and the U parity labels. If the wave function changes sign upon inversion through its center of mass, so in other words, if we invert the wave function through the center of the molecule, then we'll have, and it keeps the same sign, so if, I don't know how to write this. If it stays the same sign, then this is G. If it changes sign, then it's U. Okay, so this parity label is something that we've run into before, and this will now appear as part of the term symbol. But I want to caution you something. This will only appear if I have a homonuclear diatomic. Okay, we cannot have this symbol if we have a heteronuclear diatomic because there's no point of inversion. There's no inversion symmetry associated with it. Finally, the plus or minus that appears as a superscript here in this term symbol is something that relates to reflection symmetry in a plane that contains the internuclear axis. It doesn't have to be one particular plane, it can be any plane, but if you have a plane that contains the internuclear axis, there's a reflection of the wave function through that plane, and if it is symmetric, then it ends up being plus. If it's anti-symmetric, then it ends up being minus. This will mostly apply when we have lambda equals 0, which is a state that we would label with a sigma. So you won't really see it with any others along the way. All right, so given all of this, how would we construct one of these term symbols for a given molecule? Well, let's do H2, which is a pretty simple case because H2 has a configuration of simply 1 sigma G2. That's a really easy configuration. So this is our electronic configuration. All right, and we can basically say there's one microstate that's possible in this case, and that one microstate ends up having one of the electrons with a spin value of plus 1/2, and its m sub lambda value equal to 0, and the other electron with its spin value of minus 1/2, and its m sub lambda equals 0. So the way we can get our total spin and our total lambda is by adding these up. So in this case, spin is equal to plus 1/2 minus 1/2, so it's 0. Lambda is going to be the sum of these two, so that'll be 0. Another way to look at this is lambda is equal to the sum of m sub lambda, and this is what we've really drawn here is sum m sub lambda, but it's the absolute value of that, so it's going to be 0. So we have 0 and 0, which makes things really easy. We know we're going to have a sigma state. 2s plus 1 represents 1. So the term symbol in the case of hydrogen is going to end up being a singlet sigma state. And we know that the bonding orbital, a sigma bonding orbital, has symmetry of G. So this will be singlet sigma G would be the term symbol for hydrogen. So that's a really easy one to do. Well, let's do one a little bit more complicated. Okay, I've drawn up here the electron configuration for NO as we found it before. Now, I'll point out that whenever we have a filled subshell, which we do with these two, and we have basically filled these parts of the orbitals, we're always going to end up from all of those filled subshells essentially S equals 0, whoops, let's cross that out, S equals 0, and we'll have as many negative m sub lambdas as we'll have positive m sub lambdas, so the lambda will be equal to 0 too for all of those filled subshells. So just like the atomic case, we can focus on the unfilled parts of the electronic configuration. Well, this one is particularly easy because we have a pi star from a 2p orbital, and there's one electron, so ms of that one electron is a half, and the lambda in this case is 1. So we're going to have a pi term symbol. With the ms of a half, there's two possibilities. It could be a half or minus a half, which always tells you it's a doublet, but 2s plus 1 was going to equal to 2. So this will be a doublet pi state. And then if I were to calculate the omega value, omega is going to range from m plus s to lambda plus s to lambda minus s. So in this case it would be 3 halves, in this case it would be 1 half. So I'm going to have two term symbols that look like this for my NO molecule. And as it turns out, applying Hund's rules, we would find that this one is in fact the lower energy of the two, because this is a less than half filled subshell within the molecular terms. So this gives you an idea of how to construct those molecular term symbols. In general, they're easier to do than the atomic term symbols, so I hope you'll find these to be relatively easy to put together.